Okay guys, well this is week 7, video number 3. So there's not too much new stuff, hardly any really. This is just me going over some homework problems from chapter 7. So I'm just going to start off with some homework problems from chapter 7, try to cover almost everything that is addressed in the chapter 7 homework problems. But towards the very end there is some new stuff, and that's exothermic versus endothermic reactions and drawing reaction energy diagrams. So if you're just on this video looking for new material, go towards the end and you can find it there. Okay, so some homework problems from chapter 7. This is number 3B. So it says calculate the number of SO2 molecules in 1.28 moles of SO2. So 1.28 moles, you start with what you're given, put it over 1. And to get from moles to molecules, we have to use Avogadro's number. And I see that I have to have 1 mole for every 6.02 times 10 to the 23rd molecules, SO2. Okay, so started with 3 sig figs. My answer is 3 sig figs, 7.71 times 10 to the 23rd molecules. 7.4a, calculate the number of lithium atoms in 4.5 moles of lithium. So I start with what I'm given, put it over 1, 4.5 moles of lithium. For every 1 mole of lithium, I have 6.02 times 10 to the 23rd atoms. Started with 2 sig figs. My answer has 2 sig figs, 2.7 times 10 to the 24th atoms. Now, notice the difference between molecules and atoms in 7.3b and 7.4a. That's because SO2 is a molecule, whereas Li was an atom. So 7.4d, calculate the moles of C2H6 in 3.75 times 10 to the 23rd molecules. This time I'm starting with molecules, start with what I'm given, put it over 1. Because I'm starting with molecules, now I have to have Avogadro's number on the bottom. For every 6.02 times 10 to the 23rd molecules of C2H6 on the bottom, there are 1 mole of C2H6. Started with 3 sig figs, my answer is 3 sig figs, 0.623 moles C2H6. Make sure you can replicate 7.4d on your calculator. Sometimes dividing by Avogadro's number is difficult for some people. C, this is 14C. Wasn't assigned, but you have a lot of problems like it. Calculate the molar mass. Anytime you're asked to find the molar mass, you just add up all of the elements that you see in the formula from the periodic table. And as you can see, I like to report my molar masses to the hundredths place, like the last answer was 183.00 grams per mole. Top of page 2, this is number 11 from chapter 7. It wasn't assigned, but it's very similar to the ones that were. So chapter 7, number 11C, find the molar mass of Mg3PO42. Notice the parentheses around PO42. That's going to give me 8 oxygens. Be very careful. So I add all this stuff up. I got those numbers from the periodic table, and Mg3PO42 weighs 262.87 grams per mole. Again, I like to report my molar masses to the hundredths place. So this is chapter 7, number 22. D says, calculate the mass in grams of 0.145 moles of C2H6O. So I need to go from moles, that's my start with what I'm given, put it over 1, moles to grams. To go from moles to grams or grams to moles of the same substance, we use the periodic table. So I start with what I'm given, put it over 1.145 moles C2H6O. Now for every 1 mole on the bottom, we have 46.08 grams C2H6O on the top. You notice on the right there with the little writing, it's 46.08 G/mole. But when you use dimensional analysis, to start with what you're given, put over 1 and move left to right, it's grams all over 1 mole. So be careful on that. Whenever I start with 3 sig figs, I end up with 3 sig figs. The answer is 6.68 for number 22. 26D, calculate the number of moles in 308 grams of BaSO4. All right, so now we're just going the other way. This is the opposite of 22. Start with what you're given, put it over 1, 308 grams, and now I got to get into moles. So for every 233.37 grams of BaSO4 on the bottom, I have 1 mole of BaSO4. It's very important to write out all your units when you start with what you're given, put it over 1, and move left to right. You're following the units more than you are the actual values. Okay, so 38 is a little different. This is we're moving on now to how to balance equations. So this is an equation, Sb2S3 plus HCl. So let's see, I see two SBs on the left, so let's put a coefficient 2 on the right. That gives me 6 Cl's. Let's put a 6 in front of HCl, and then the 6H works out with the 3H2S. Okay, so this is a double replacement reaction, right? The SB and the H flip-flop and take the other anion. So D from the same problem says Fe2O3 plus C yields Fe plus CO. So I see two Fe's, I put the 2 coefficient on the right, and then I just kind of work my way through on this one. This is a what type of reaction? This is a single replacement reaction. Okay, the carbon comes in, kicks out the iron, and singly replaces the Fe to take oxygen for itself. Number 56, A, it says ammonia is produced by N2 plus 3H2 yields 2NH3. And these are all gases. And it says, here is the question. So now we're going to start to use moles to grams, grams to moles, etc., but using balanced equations as well. This is stoichiometry now. So how many moles of H2 are required to react with 1.8 moles of N2? Start with what you're given, put it over 1. 1.8 moles of N2 over 1. Balanced equation, for every 1 mole of N2, there are 3 moles of H2. Cancel units, boom. Started with 2 sig figs, end up with 2 sig figs, 5.4 moles of H2. It's very nice to start off in moles, because from moles I can go to grams. From moles I can go to molecules, atoms. When in doubt, convert to moles. 60, B, given N2 plus 3H2 yields 2NH3. The question is, how many molecules? Okay, this is a little different. This isn't moles, it's molecules. Molecules usually means I need Avogadro's number. How many molecules of H2 are required to react with 2.80 grams of N2? Start with what you're given, put it over 1 every time for this class. 2.80 grams of N2 over 1. For every 28.02 grams of N2, there are 1 mole of N2. That's from the periodic table. 28.02 is the molar mass. Now I'm in moles of N2. Balanced equation, for every 1 mole of N2, there are 3 moles of H2 in the balanced equation. Now I'm in moles of H2. 1 mole of H2 contains 6.02 times 10 to the 23rd molecules of H2, and my answer is 1.80 times 10 to the 23rd molecules. And we started with 3 sig figs, so we ended up with 3 sig figs, okay? All right, question 62. Given Fe2O3 plus 3 carbon yields 2 Fe plus 3 moles of carbon monoxide. Now I see a coefficient 323 in there, so I know it's already balanced. It says, how many moles of CO are produced when 1.807 times 10 to the 24th atoms of carbon reacts? So I see the 1.807 times 10 to the 24th atoms. I put that over 1. That's my start with what I'm given, put it over 1. Notice I write out atoms of carbon. I got atoms C. I need to follow the units all the way. So for 1 mole of carbon contains 6.02 times 10 to the 23rd atoms. That gets me into moles. And then I have 3 moles of carbon for every 3 moles of CO in my balanced equation. I started with 4 sig figs. My answer must be in 4 sig figs. 3.002 moles of CO. All right, C. From the same balanced equation up there, it says, how many atoms of Fe can be formed when 6.00 grams of Fe2O3 reacts? Remember, atoms is the same thing as molecules. Because they're saying atoms, we know they're referring to an element, Fe, or carbon. If they were talking about CO, they'd have to use molecules instead of the word atoms. 6.00 grams of Fe2O3, start with what I'm given, put it over 1. If I divide by the molar mass of 159.70, that puts me into moles of Fe2O3. For every 1 mole of Fe2O3, there are 2 moles of Fe in my numerator, balanced equation. And then 1 mole of Fe contains how many atoms? 6.02 times 10 to the 23rd atoms. My answer, 4.52 times 10 to the 22nd atoms of Fe. All right. Because I have Avogadro's number, 6.02 times 10 to the 23rd in my numerator, I know my answer is going to be really large, and it was 4.52 times 10 to the 22nd atoms. All right, this is some new material here, okay? This is kind of like a new lecture material at the end of this video. Energy in chemical reactions. So, when a chemical reaction occurs, it's either going to release energy or it's going to require energy. So when a chemical reaction occurs, energy in the form of heat is either released is exothermic, or it's absorbed. Absorbed means required. Okay, released means like produced or gives off. So exothermic reactions, they release heat. If they release heat, a exothermic reaction in the test tube is going to feel hot. The test tube gets hot. Here's an example. You got 2 aluminum plus Fe2O3 yields 2 Fe plus Al2O3 and plus 850 kilojoules. That's because that's the energy released, right? Kilojoules is energy. Now, the way I usually write it is I just write the balanced equation the second way here. 2Al plus Fe2O3 yields 2Fe plus Al2O3. And then because energy is released, the change in energy is minus 850. And I'm putting that energy into a reaction energy diagram right here, where EA is my activation energy. That is the energy that I have to overcome in order for 2 colliding reactants to move towards products. Okay, so activation energy, I will define it right here for you. It is the energy needed to break the bonds of reactants and then continue downhill towards products. Now here you notice that the products are lower energy and the delta E is a negative 850. This is what an exothermic reaction energy diagram looks like, okay? Well, if the first one is exothermic reactions and heat's released, the second one is endothermic reactions, where heat is absorbed or heat is required or heat is needed. It's absorbed, and if you were to run a reaction like this in the test tube, it would feel cold to the touch because heat is leaving the surroundings and going into the reaction system. So I've written the 26 kilojoules as a reactant there because that's needed, it's absorbed. All right, now the way I like to do it and the way that most textbooks do it is they like to write the delta E after the equation. So here I have NH4NO3 solid. The presence of water becomes NH4NO3 aqueous. Okay, so just the act of dissolving NH4NO3, this is kind of like in those cold packs that you break. The delta E here is plus 26 kilojoules because the energy is required or absorbed. Now, the reaction energy diagram for this one is different. You'll notice that the reactants starts at one level and the products are higher up. That still doesn't mean we still have to overcome that activation energy barrier, right? We have to collide our reactants with enough energy to get up and over that EA and downhill. All right. So the reaction energy diagram that I've drawn here is for an endothermic reaction, and the products are higher than the reactants, and the delta E is plus 26 kilojoules. Now, just a note, in both of those reaction diagrams I've just drawn, and in both of these sample balanced equations I drew, it says here, note, in both exothermic and endothermic reactions, the activation energy barrier, EA, that hump must be overcome in order for the reaction to move forward towards products. I don't know if you've ever been to the video arcade and you played skee ball, but when you roll the skee ball, it's got to go up and over that hump before it can move on and go in, okay? So three conditions have to be met in order for you to overcome this activation energy barrier, this big EA hump that you see on both of the reaction energy diagrams. First, the reactants have to collide, and then second, the reactants have to collide with enough force, right? So that when they have enough force, they break the reactant bonds and overcome this activation energy, and then they can form product bonds. And then the third one is that reactants must be aligned or oriented properly. So if this is what's needed for two reactants to collide, you wouldn't want them to collide like this. You'd want them to be aligned properly so that they can move to products. All right, so let's do just a sample calculation on this new stuff, this exothermic and endothermic reactions and reaction energy diagrams, and what affects the rate of a reaction as well. So this is problem 76 from your assigned homework problems. It says, how would each of the following change the rate of reaction shown here? In other words, what would speed up or slow down this reaction? So the first thing I need to do is balance it. Always make sure your reactions is balanced, okay? So I am going to do an A, B, C, D, and then we will decide if we are going to increase or decrease the rate of the reaction. So A, if I add more nitrogen monoxide, I am adding more NO. I'm adding more of a reactant. I've got more reactants capable of colliding. This is going to increase the rate of reaction. B says decreasing the temperature. Well, if I decrease the temperature, these guys are going to be sluggish and not move as fast. We're not going to have as many effective collisions, so it would decrease reaction rate. If I remove H2, I'm taking away some of the reactants, which means I'm taking away some of the guys I need to collide. This would decrease reaction rate. Adding a catalyst, we haven't talked too much about a catalyst, but just think of it in everyday life. If you know of somebody or some sort of cause that's a catalyst for change, they're helping make changes in everyday life quicker, more efficient, or faster. So if you add a catalyst, you're increasing the reaction rate. Okay, so this has been a video on just basically Chapter 7 homework problems and a little bit of new information there on the energetics of reactions. And hopefully it helps you. Hopefully you watch this before you take the quiz and before you do the lab, because this will be a big help for both of those. Okay.